Hello, I'm Sofia Vey from Aristotle University of Thessaloniki, and in this lesson I will demonstrate how we use energy forecasting in TRINEFLEX to support industrial energy flexibility. Forecasting here means predicting future consumption or generation so an industrial site can plan flexible operation rather than react at the last minute. We implemented this for two pilots, ADAP for wastewater and Halcor for copper processing. These forecasts fit the TrineFlex smart contract engine, which needs reliable predictions to validate and execute flexible commitments. We did not build one-off models. We built a reusable pipeline that works across process industries. The steps are always the same. Collect historical data, reprocess it into a trustworthy time series, train a model, evaluate it on unseen periods, expose forecasts via an API, and then the smart contract engine can consume them automatically. Cross pilots, what changes is mainly the preprocessing logic and the model choice, not the overall architecture. Industrial forecasting success is mostly a data problem. What we need is a consistent time series, either consumption or production, a stable timestamp or resolution, and enough history to learn weekly and seasonal patterns. Typical pain points we faced are long gaps from sensor failures, extreme spikes or outliers, false zeros that mean missing or idle, and mismatched resolution like noisy 15-minute data versus stable daily aggregates. Now, in our two pilots, we faced two very different realities. In ADAP, the challenge was turning many raw SCADA signals into a reliable consumption dataset, while in Halcor, the challenge was preserving real volatility while dealing with very large gaps. In ADAP, we had hundreds of raw SCADA signals across different files. Some were on and off status, others were analog values like inverter percentage, so we had to build a data fusion step. Firstly, we synchronize timestamps. Then we map each tag to the correct equipment specification and convert raw operational signals into a ground truth consumption time series per process. The key takeaway is basically that before we forecast, we must define what consumption means operationally and how it is computed from our signals. For ADAP consumption forecasting, we trained models per process because each process behaves differently. Some loads are smooth, others, like sludge recirculation, switch sharply between zero and high demand. That's normal operational behavior and not noise. So what we learned is that weather didn't improve this specific forecast much, but longer operational history did because the main driver was operator schedule but not climate. So the practical message is if our process is schedule driven, we get the biggest gains by capturing enough history and stable operational patterns. On the supply side, we forecasted site-wide photovoltaic production. We needed to test the future pilot period using historical data, so we used a temporal shift. We moved valid photovoltaic production timestamps forward by 1 year and then compared predictions against the shifted future period. The result is a closed match, meaning the model captures most of the variability in photovoltaic output. Operational takeaway is that the photovoltaic forecasting helps decide when to schedule energy-intensive tasks to match renewable availability and reduces risk when committing flexibility. Halcor is highly volatile by nature, since there are many on and off events, batch changes, and product mix. Here, the danger is oversmoothing because volatility is the reality we must forecast. We also had large gaps. Standard interpolation creates artificial flat lines, which misleads models. So we used year-over-year gap filling. If days were missing in 2024, we filled them with the same dates from 2023. This preserves the factory's typical variability, so the model trains on realistic dynamics. The method works best when seasonal operating patterns are compatible year to year. We forecasted Halcor at multiple resolutions. Why? Because resolution should match the decision. For 15-minute and hourly forecasts, we use them as mainly for peak visibility, and operational monitoring. Daily forecasts are better for planning and contract validation because they are less sensitive to timing noise. We used XGBoost here because it handles sudden on and off transitions better in this dataset. Daily performance was strong and stable, which is exactly what the smart contracts required. Once validated, we operationalized the models as live APIs. The workflow we followed is validate using historical ground truth plots, then retrain on all available data, and deploy as a service that always outputs the next 16 days. From a user perspective, you select a machine or process and the granularity, and you receive forecast values through a standard JSON interface ready for dashboards, optimizers, or the smart contract engine. And let me close with a practical checklist. Start with a decision. So, what flexibility action are you enabling? Then identify the asset or process and confirm you have reliable timestamp, consumption, or production data. Audit the pain points, gaps, spikes, false zeros, and resolution consistency. Choose the right resolution for the decision. Daily for planning, higher frequency for operations. Validate on historical periods before deployment. And finally, expose forecasts via API with monitoring and fallbacks. That's how forecasting becomes a truly operational tool for energy flexibility.